The ice of the Arctic Ocean does not conceal secrets for the sake of strategy, but for the sake of survival. In the crushing darkness beneath the polar cap, the Soviet Union hid a weapon designed to end human civilization long after its own leaders were dead. This was not an act of aggression, but a terrified guarantee that the silence of the grave would be answered by fire. To understand the machine known to the West as the Delta III, one must first understand the environment that necessitated its creation. The Arctic Ocean is a hostile, alien world, defined by a darkness that lasts for months and temperatures that freeze the sea into a shifting, grinding continent of ice. Beneath this frozen ceiling, the water is black, calm, and incredibly deep. It is a place of absolute isolation, where the only sounds are the groaning of the ice pack shifting overhead and the distant, rhythmic ping of sonar searching through the thermal layers. For decades, naval strategists viewed this region as a barrier, a frozen wall that separated the superpowers. But in the 1970s, the Soviet Union transformed the Arctic into a fortress. They called it the Bastion. It was a strategic concept born of necessity and fear. The Soviet naval leadership realized that the open waters of the Atlantic were a killing field. Their submarines, while numerous, were often louder than their American counterparts. If they tried to cross the gap between Greenland, Iceland, and the United Kingdom to reach their patrol zones off the American coast, they were hunted. They were tracked by networks of seabed hydrophones and trailed by hunter-killer submarines that could hear them coming from miles away. The Kremlin faced a terrifying mathematical problem. If a nuclear war began, the United States would likely strike first, targeting the missile silos on land. The Soviet retaliation depended entirely on their submarines surviving that initial onslaught. But if those submarines were being tracked and sunk before they could launch, the Soviet Union effectively had no deterrent. They were holding a gun that they could not fire. To solve this, they decided to stop running the gauntlet. Instead of sending their submarines to the enemy, they would bring the launch sites home. They would park their ballistic missile submarines in the deep, ice-covered waters north of Russia, protected by the entire might of the Soviet Northern Fleet and the impenetrable shield of the polar ice cap. However, the submarines of the early 1970s were ill-equipped for this role. The Soviet fleet was a mixture of ambition and dangerous compromise. The older Project 658, known to NATO as the Hotel class, and the Project 667A, or Yankee class, were formidable on paper but fragile in reality. They required the crew to battle the ship as much as the enemy. These vessels were plagued by mechanical reliability issues, leaking radiation shielding, and volatile liquid fuel missiles that required constant monitoring. Historian Norman Polmar, a leading authority on the Soviet Navy, has noted that during this era, the primary danger to a Soviet submarine crew often came from their own technology. The reactors were powerful but temperamental. The missile tubes were prone to seal failures. The strategic planners in Moscow lived with the constant anxiety that their deterrent force was a paper tiger, a fleet that looked impressive in a parade but might fail in the chaos of a real nuclear exchange. The central question haunting the Soviet Ministry of Defense was simple but chilling. If the order came to destroy America, would the missiles actually fly, or would the submarines be burning wrecks on the ocean floor before they could turn their keys? This anxiety was compounded by the rapid advancement of American technology. By the early 1970s, the United States Navy was deploying the Poseidon C-3 missile. This weapon allowed American submarines to strike targets deep inside the Soviet Union from the safety of their own home waters. The Americans had achieved the holy grail of deterrence, a secure, survivable second strike capability. The Soviets were lagging behind, forcing their crews to sail into harm's way just to get within range. In 1973, the Soviet leadership decided that the era of compromise was over. They needed a new weapon system that could match the range of the Americans and the reliability required for the Bastion strategy. They did not just want an upgrade, they wanted a guarantee. The design bureaus were ordered to develop a new submarine-launched ballistic missile. The result was the R-29R. To the West, it would be known as the SSN-18 Stingray. It was a masterpiece of lethal engineering. It was the first Soviet sea-based missile capable of carrying multiple independent warheads, known as MIRVs. This meant that a single missile could strike 3 or 7 different cities simultaneously. But the most critical feature of the R-29R was its range. It could travel 4,000 miles. This number changed the geography of the Cold War. A submarine armed with these missiles did not need to sail to the coast of New York or Washington. It could sit in the Barents Sea or the Sea of Okhotsk or under the ice of the North Pole and still hit any target in the Northern Hemisphere. The existence of this missile created an immediate engineering challenge. The R-29R was massive. It was taller and heavier than the missiles carried by the existing Yankee and Delta YY-class submarines. You could not simply shove this new weapon into an old hull. The submarine had to be redesigned around the missile. The task fell to the Rubin Design Bureau, led by the legendary chief designer Sergei Kovalev. Kovalev was the architect of the Soviet strategic fleet, a man who understood that a submarine was more than just a boat. It was a launch platform for national survival. He looked at the specifications for the new missile and realized that the existing hull forms were insufficient. He proposed a radical evolution of the existing Project 667 design. The new submarine would be longer, heavier, and more complex than anything that had come before. It would be designated Project 667 DDR and named Kalmar, the Russian word for squid. NATO would give it a more clinical designation, the Delta III. The visual profile of the Delta III was defined by the missile it carried. Because the R-29R missiles were so tall, they could not fit entirely inside the pressure hull. They protruded upwards, forcing the designers to build a massive raised casing behind the conning tower to streamline them. This feature, known as the turtleback, gave the submarine a hunched, aggressive silhouette. It was not a sleek, hydrodynamic shape designed for speed. It was a shape designed for volume. It was a warehouse for the apocalypse. The construction of these vessels began at the Severodvinsk shipyard in the mid-1970s. The scale of the effort was immense. The Soviet Union was pouring a significant percentage of its gross national product into the creation of these ships. They were building them not by the ones or twos, but in a production line that churned out nuclear-powered giants with frightening regularity. The Delta III was designed to be the workhorse of the apocalypse. It was 155 meters long, longer than a football field. It displaced 13,000 tons when submerged. It was powered by 2 nuclear reactors, giving it the ability to stay underwater essentially forever, limited only by the amount of food on board and the sanity of the crew. But the true innovation of the Delta III was not just its size or its range, it was its fire control system. Previous Soviet submarines had a fatal flaw in their launch sequence. Due to the complexity of stabilizing the submarine during a missile launch, they could often only fire 1 or 2 missiles at a time. After firing, the submarine would lose trim, bobbing to the surface or sinking too deep, forcing the captain to spend precious minutes restabilizing the boat before firing the next salvo. In a nuclear war, minutes are an eternity. While the captain was fighting to level his ship, American anti-submarine forces would be triangulating his position. The smoke trail of the first missile would act as a giant arrow pointing directly to the submarine. A slow launch rate meant the submarine would likely be destroyed before it could empty its silos. The Delta III changed this. It was fitted with the D9R missile complex, a system that integrated the ballast tanks, the trim pumps, and the missile tubes into a single automated network. For the first time, a Soviet submarine commander could theoretically launch all 16 of his missiles in a single continuous ripple. This capability, known as a full salvo, was the strategic breakthrough the Kremlin had been waiting for. It meant that even if a Delta III was detected, even if it was being hunted, it could unleash its entire payload, dozens of nuclear warheads, before an enemy torpedo could reach it. It compressed the timeline of Armageddon from an hour down to barely a minute. As the first Delta III slid into the freezing waters of the White Sea in 1976, the balance of power shifted. The Soviet Union finally had a credible, survivable second strike platform. They no longer had to send their sons to die off the coast of Bermuda. They could keep them home, hidden under the ice, safe in the Bastion. But this safety came with a new set of challenges. Operating in the Arctic is not like operating in the open ocean. The ice is a physical ceiling that traps the submarine. To launch its missiles, the Delta III had to be able to break through that ceiling or find a way to fire through the cracks. It required a new kind of seamanship, a new level of navigation, and a crew capable of enduring months of darkness in the most isolated place on Earth. Historian Pavel Podvig, an expert on Russian strategic forces, argues that the deployment of the Delta III marked the moment when the Soviet Union truly achieved strategic parity with the United States. It wasn't just about the number of warheads, it was about the certainty of their delivery. The Delta III was the machine that convinced the West that a first strike was impossible because the retaliation was now guaranteed. The introduction of the Kalmar class signaled a change in the psychology of the Cold War. The frenetic, desperate race to catch up was over. The Soviets had arrived. They had built a wall of nuclear fire around their northern coast, and the Delta III was the guard tower. Yet inside the titanium and steel hulls, the human reality was still fraught with danger. The crews of the Delta III were elite, but they were still operating a machine filled with high-pressure steam, radioactive isotopes, and volatile rocket fuel. The Bastion might have protected them from American destroyers, but it could not protect them from a short circuit, a burst pipe, or a navigational error in the uncharted canyons of the Arctic floor. The Delta III Sovietist a significant leap forward, but it was still a Soviet machine built with the philosophy that performance mattered more than comfort and the mission mattered more than the men. As these submarines began their patrols, slipping beneath the ice pack to disappear for months at a time, they carried the weight of a superpower's survival in their missile tubes. They were the silent sentinels of the Brezhnev era, massive, brooding, and dangerous. They patrolled a world of white silence, waiting for a message that would order them to turn the key and break the ice. The anxiety of the early 1970s had been replaced by the cold confidence of the late 1970s. The Soviet Union had solved the problem of survival, but in doing so, they had turned the Arctic Ocean into the most heavily armed parking lot in history. If the hull of the Delta III, the fortress, the missiles inside were the reason the walls had to be built. The distinctive silhouette of the submarine, with its humped turtleback rising awkwardly behind the sail, was not an aesthetic choice. It was a physical necessity dictated by the sheer scale of the weapons housed within. Inside those 16 vertical tubes sat the R-29R, a missile that represented a quantum leap in the lethality of the Cold War. To understand the terrifying elegance of the Delta III, one must look past the steel of the submarine and into the chemistry of the rocket. In the mid-1970s, the arms race was no longer defined by how big a warhead you could build, but by how many you could fit on a single rocket. The United States had already deployed multiple independently targetable re-entry vehicles, or MIRVs, on their Poseidon missiles. This technology allowed one missile to release several warheads, each guiding itself to a different city or military base. It changed the math of nuclear war from a duel of single shots to a shotgun blast of destruction. The Soviet Union, lagging in miniaturization technology, had struggled to match this capability. Their early missiles carried only a single, massive warhead. While destructive, these single warhead missiles were vulnerable to anti-ballistic missile systems and inefficient against spread-out targets. The Kremlin demanded parity. They wanted a missile that could overwhelm any defense the Americans could construct. The Mekiev Rocket Design Bureau answered this demand with the R-29R, known to NATO as the SS-N-18 Stingray. The R-29R was a liquid-fueled monster. In the West, naval engineers viewed liquid fuel as a liability. It was toxic, corrosive, and volatile. American submarines used solid fuel rockets, which were essentially stable cylinders of propellant that could be stored safely for years. But solid fuel at the time lacked the energy density of liquid propellants. To throw a heavy payload over 4,000 miles, the Soviets needed the raw power of liquid hydrazine and nitrogen tetroxide. The Mekiev engineers accepted the risk of the fuel to achieve the range. They designed a two-stage rocket that stood 46 feet tall and weighed nearly 80,000 pounds. It was a masterpiece of compact design with the engines nestled inside the fuel tanks to save space. But its true power lay in its nose cone. The R-29R was the first Soviet sea-based missile equipped with MIRV technology. It could be configured to carry a single massive warhead with the explosive power of nearly 500,000 tons of TNT, or it could split that power into 3 or even 7 smaller, independent warheads. This flexibility meant that a single Delta III submarine carrying 16 of these missiles was not just targeting 16 locations. It could theoretically strike more than 100 separate targets. A single boat could target every major military installation on the east coast of the United States. The turtleback hump on the submarine was not just a casing, it was a warehouse containing enough firepower to dismantle a civilization. However, carrying the missiles was only half the battle. The true engineering challenge, and the aspect of the Delta III that kept NATO analysts awake at night, was the firing system. In the previous generations of Soviet missile submarines, launching the payload was a slow, laborious process. The Yankee-class boats had to surface or hover at very specific depths. They had to stabilize the ship between each shot. The recoil of an 80-ton missile leaving the tube creates a massive hydrodynamic shock. The submarine loses weight instantly, causing it to lurch upward. The captain has to flood ballast tanks immediately to compensate, or the submarine will broach the surface, exposing itself to enemy fire. Because of this instability, older Soviet submarines typically fired their missiles in ripples of 1 or 2, with long pauses in between to retrim the boat. A full salvo of 16 missiles might take 20 minutes or more. In a nuclear war, 20 minutes is a lifetime. During that launch window, the submarine is vulnerable. The launch of the first missile creates a massive acoustic and thermal signature. It is a flare gun announcing the submarine's location to every satellite, aircraft, and hunter-killer submarine in the hemisphere. If a captain takes 20 minutes to empty his silos, he will likely be destroyed before he finishes the job. The designers of the Delta III, led by the Rubin Bureau, knew they had to compress this timeline. They developed the D9R missile complex, a fully integrated launch system that automated the ballast compensation. The D9R was a marvel of hydraulic and pneumatic engineering. It connected the missile tubes to the ballast tanks with a high-speed management system. As a missile was ejected by the gas generator at the bottom of the tube, the system instantly flooded a compensation tank with precisely the right amount of seawater to match the weight of the lost weapon. This allowed the Delta III to do something no previous Soviet submarine could do. It could launch all 16 missiles in a single, continuous salvo. The firing sequence of a Delta III is a study in organized violence. The captain gives the order. The pre-launch sequence automates. The pressure in the tubes is equalized with the outside water pressure. The heavy steel hatches on the turtleback slide open. From the perspective of a NATO satellite looking down, the opening of the hatches is the final warning. The intelligence community spent years studying the pattern. They noticed that the hatches did not open randomly. They opened in a specific sequence, often starting from the bow and moving aft, or alternating port and starboard to maintain the trim of the ship. Once the sequence begins, the submarine becomes a factory of launch. Every 14 seconds, a missile erupts from the deck. The gas generator fires, creating a bubble of steam that pushes the rocket out of the tube. The missile breaches the surface of the water. The main engines ignite, sending a pillar of fire into the sky. In under 4 minutes, the Delta III can empty its entire magazine. This capability fundamentally altered the strategic balance. It meant that even if a NATO hunter-killer submarine was trailing a Delta III, the window of opportunity to stop the launch was razor-thin. By the time the American captain detected the opening of the silo doors and fired his torpedoes, the Soviet missiles would already be in the air. The second strike was no longer a theoretical possibility. It was an operational certainty. The D9R system was tested rigorously. In one famous exercise, a Delta III fired a partial salvo, proving that the system could handle the violent shifts in buoyancy without the submarine losing control and tumbling into the depths. The stability of the platform was exceptional. The Delta III was a steady gun platform, a sniper's rifle held stable in the chaos of the ocean. However, the reliance on liquid fuel introduced a persistent, low-level danger to the crew that Western crews did not face. Solid fuel missiles, like the American Trident, are essentially inert until ignited. Liquid fuel missiles are filled with chemicals that are corrosive and toxic. The oxidizer, nitrogen tetroxide, turns into nitric acid if it touches moisture. The fuel, hydrazine, is a carcinogen that attacks the nervous system. The missile tubes on the Delta III were not just storage containers, they were chemical containment vessels. They were lined with sensors to detect leaks. The air in the missile compartment was constantly monitored. A microscopic crack in a fuel tank could release toxic vapors into the submarine, incapacitating the crew before a single shot was fired. This danger was the price of performance. The Soviet Union accepted the risk to the crew to ensure the range of the weapon. It was a doctrinal decision. The mission of deterrence was worth the hazard of the chemistry. The intelligence agencies of the West watched the development of the Delta III with a mixture of respect and alarm. They tracked the test launches from the White Sea to the impact ranges on the Kamchatka Peninsula. They measured the telemetry of the warheads as they re-entered the atmosphere. What they saw confirmed their fears. The R-29R was accurate. Its stellar inertial guidance system, which used the stars to update its position in flight, gave it a circular error, probable, CEP, of roughly 900 yards. This was not accurate enough to destroy a hardened missile silo, but it was more than accurate enough to destroy a city, a port, or an industrial center. The Delta III was a counter-value weapon. In nuclear strategy, counter-force weapons target the enemy's military. Counter-value weapons target the enemy's society. The Delta III was designed to hold the American economy and population hostage. The deployment of these submarines in the late 1970s completed the Soviet nuclear triad. For the first time, the Kremlin could look at the map and see a secure, redundant deterrent. If the land-based missiles were destroyed, the Delta III would still be there. If the bombers were shot down, the Delta III would still be there. The boat itself was designed to support this long-range mission. It carried supplies for 90-day patrols. The crew of 130 men lived in conditions that were Spartan by Western standards but luxurious by Soviet ones. They had better food, more showers, and a higher standard of living than most civilians back in Moscow. This was necessary to maintain morale during the long, silent months under the ice. But the most significant aspect of the Delta III was not just that it could fire everything at once. It was that it could do so from anywhere. Previous submarines had to travel to specific launch boxes, areas of the ocean that had been pre-surveyed to ensure the navigation systems were accurate. The Delta III Sasarafs, equipped with the R-29R, had a range that turned the entire Arctic Ocean into a launch box. It could fire from the pier, it could fire from the Barents Sea, it could fire from the North Pole. This flexibility made the Delta III first true Bastion submarine. It allowed the Soviet Navy to pull their defensive perimeter tight against their own coast. They didn't need to control the Atlantic, they just needed to control the Arctic. As the 1970s drew to a close, the Delta III became the backbone of the Soviet strategic fleet. 14 of these vessels were built, a production run that flooded the northern waters with nuclear capability. They became the silent, invisible queens on the chessboard, pieces that could not be removed without triggering the end of the game. The fire from the deep was real. The capability was proven, but a missile is only as good as the system that tells it where it is. To make the Delta III truly effective under the ice, the Soviet engineers had to solve one more problem. They had to figure out how to navigate a submarine for months without ever seeing the sky, the stars, or a GPS satellite. They had to teach the blind how to see. This leads us to the next great innovation of the Project 667BDR, the navigation system that allowed the submarine to disappear from the face of the Earth, yet know exactly where it was within a matter of feet. To a submarine commander operating beneath the polar ice cap, the concept of location, is a fluid, terrifying variable. In the open ocean, a ship can look at the stars, triangulate radio beacons, or in the modern era, listen to the digital chatter of GPS satellites. But under the ice, the world is sealed. There is no sky. There are no stars. Radio waves do not penetrate the frozen ceiling. There is only the black water, the white roof of the ice, and the silent, crushing pressure. For a hunter-killer submarine, exact geographic precision is a luxury. If you are hunting another ship, you navigate relative to the target. But for a ballistic missile submarine like the Delta III, knowing your position is not just about navigation, it is about ballistics. A nuclear missile is a mathematical equation. It calculates a trajectory based on a starting point and an ending point. If the computer believes the submarine is 1 mile east of its actual location, the warhead will land 1 mile east of the target. In the grim calculus of nuclear war, that error is the difference between destroying a missile silo and blowing up an empty field. Before the arrival of the Delta III, the Soviet Navy faced a crippling navigational paradox. Their gyroscopes, the spinning mechanical hearts of the navigation system, suffered from drift. Over time, due to friction and the rotation of the Earth, a gyroscope loses its accuracy. After a few days submerged, the error accumulates. To reset the system, the submarine had to get a fix. Getting a fix required the submarine to approach the surface. It had to raise a periscope to shoot a star, or raise an antenna to catch a radio signal from the Cicada navigation satellites. This moment of calibration was the moment of maximum vulnerability. To fix its position, the submarine had to reveal its position. It had to break the acoustic silence. It had to bring its hull close to the surface where magnetic anomaly detectors and thermal sensors could find it. The Soviet strategists realized that their Bastion strategy, hiding under the ice, was useless if the submarines had to poke holes in the ice every 48 hours to ask for directions. They needed a submarine that could stay submerged deep and dark for weeks or months without ever looking at the sky, yet still know exactly where it was within a margin of a few hundred meters. The solution was the navigation complex known as the Tobol M2. Installed on the Project 6667BDR, the Tobol M2 was not just a compass, it was a heavy, hardened computational beast. It integrated data from multiple sources to create a best guess that was terrifyingly accurate. It used advanced electrostatic gyroscopes that floated in a vacuum, reducing friction to near zero. These gyroscopes could spin for weeks with minimal drift, allowing the Delta III to run silent and deep for periods that were previously impossible. But the true genius of the system lay in how it read the world outside the hull. Since the submarine could not look up at the stars, the engineers taught it to look down at the mud. The Delta III was equipped with a revolutionary hydroacoustic system called the Schmel Bumblebee. This was a high-resolution photometer and seabed profiler. In the West, similar technology was being developed under the name terrain contour matching. The concept was simple in theory, but staggeringly complex in execution. The Soviet Navy spent decades mapping the floor of the Arctic Ocean. Specialized hydrographic ships crisscrossed the Barents and Kara Seas, firing sonar pulses into the deep, building a three-dimensional map of every underwater canyon, ridge, and seamount. This data was digitized, a massive undertaking in the 1970s, and loaded into the memory banks of the Tobol computer. As the Delta III patrolled, the Schmel system would ping the bottom. It would read the texture and the topography of the seafloor. The computer would compare this real-time data against the stored digital maps. If the submarine saw a ridge that matched the map at coordinates X and Y, it knew exactly where it was. It was navigation by Braille. The submarine was feeling its way through the dark, reading the landscape of the Earth itself. This capability fundamentally changed the operational profile of the Soviet strategic fleet. A Delta III could leave its base in Gromyka or Yagranaya, dive deep, and disappear. It did not need to come to periscope depth. It did not need to trail a floating wire antenna on the surface. It could loiter in the deep trenches, hovering at 300 meters, completely disconnected from the surface world. This blind navigation severed the link between the submarine and the atmosphere. It turned the Delta III into a true spaceship of the deep. For the NATO anti-submarine forces, this was a disaster. American satellites, which scanned the ocean for the thermal scars of surfacing submarines or the electronic noise of navigation fixes, suddenly had nothing to see. The Delta III went down, and it didn't come up until the patrol was over. The Tobol M2 also integrated with the Paris-Sale satellite constellation, the Soviet equivalent of the American transit system. While under the ice, the submarine could not easily receive these signals, but the system allowed for rapid realignment if the submarine found a polinia, an opening in the ice. The Delta III could pop a specialized communications buoy through a thin layer of ice, grab a data burst from space in seconds, reset the gyros, and vanish again. However, this technological leap placed an immense psychological burden on a single man, the navigator. In a surface ship, the navigator is an officer who advises the captain. On a ballistic missile submarine, the navigator is the gatekeeper of the apocalypse. If his math is wrong, the missiles are useless. The pressure on the navigational department of a Delta III was crushing. They worked in a sealed room, surrounded by humming cabinets of electronics, constantly monitoring the drift rate. They lived in a world of pure abstraction, moving a digital dot across a digital map, trusting that the physical ship was actually where the computer said it was. The consequences of a navigational error were not just tactical, they were political. If a Delta III launched a missile with a bad alignment, the warhead might land on a neutral country, or worse, on a Soviet ally. The navigator's log was the holy scripture of the patrol. The integration of the Tobol M2 with the D9R missile system meant that the launch data could be updated continuously. In older submarines, preparing a firing solution took time. The coordinates had to be manually input. On the Delta III, the navigation computer fed position data directly to the missile guidance units every second. The missiles were always aware of where they were. They were hot, ready to fly the moment the hatch opened. This continuous readiness created a new strategic reality known as launch on warning. Because the Delta III knew its position instantly, it could fire its missiles within minutes of receiving the order. It did not need to spend time maneuvering to a pre-surveyed launch point. It could fire from wherever it happened to be, even if it was drifting sideways in a current or turning. The Schmel system also provided a defensive advantage. By mapping the seabed with such precision, the Delta III could hide in the acoustic shadows of underwater terrain. The captain could position his submarine behind a seamount or inside a canyon, masking his engine noise from American listening posts. The ocean floor became a landscape of cover and concealment. But operating blindly in the Arctic had physical risks that no computer could fully mitigate. The ice above was not a smooth sheet, it was a chaotic, jagged ceiling. Ice keels, massive ridges of ice forced downward by the pressure of the pack, could extend nearly 100 feet below the surface. If a Delta III displacing 13,000 tons struck an ice keel while maneuvering, the result would be catastrophic. The sail could be crushed, the missile hatches could be jammed, and the acoustic sensors could be stripped away. To counter this, the Delta III was equipped with upward-looking sonar. This system, known as NORCA, constantly scanned the ice canopy. It painted a picture of the ceiling, looking for thick ice to avoid and thin ice to break. The submarine moved through a vertical tunnel sandwiched between the rocky bottom, mapped by Schmel, and the frozen roof mapped by NORCA. It was a claustrophobic, three-dimensional maze. The crew lived in a state of constant, low-level tension. They were flying an airplane through a canyon in the dark on autopilot. The success of the navigation systems on the Delta III convinced the Soviet leadership that the Bastion strategy was viable. They poured resources into mapping the Arctic. The hydrographic service of the Soviet Navy became one of the most important, yet secretive branches of the military. Their charts were top-secret state documents. To lose a chart of the Barents Sea floor was considered as grave as losing a cipher machine. As the 1980s approached, the Delta III fleet became the ghosts of the North. They established a pattern of continuous at-sea deterrence. At any given moment, multiple Delta IIIs were on patrol, moving slowly through the deep trenches of the Arctic, their gyroscopes spinning in vacuums, their computers reading the mud. They achieved the ultimate goal of the submarine. They became a rumor. NATO knew they were out there. They could count them leaving the piers at Yagranaya. But once they passed the breakwater and submerged, the trail went cold. The ocean is too big and the acoustic environment of the Arctic is too noisy to find a silent hole in the water that knows exactly where it is going. The Delta III had solved the problem of where. It knew its place in the world with a precision that was unprecedented. But knowing where you are is only half the battle. The other half is being able to fight from that position. The Arctic offered protection, but it also offered a barrier. The ice was a shield, but it was also a cage. To launch the missiles, the submarine had to breach the surface. The R-29R missile could not fly through 10 feet of ice. This leads to the next great operational challenge of the Project 667 BDR, the ability to turn the submarine into an icebreaker. The Soviet engineers had given the boat the eyes to see the ice. Now they had to give it the strength to smash it. The navigation systems could guide the ship to the firing position, but it would require brute force, reinforced steel, and nerves of ice to open the silo doors to the sky. The eyes of the blind had done their job. Now, the frozen fortress had to be breached from the inside. The Arctic Ocean is the only battlefield on Earth where the sky is solid. For the crew of a Delta III submarine patrolling the high latitudes, the world is defined by a ceiling of shifting, groaning ice that can be 10 feet thick or more. This frozen lid is the ultimate shield against the prying eyes of American satellites and the sonar buoys of NATO aircraft. But for a ballistic missile submarine, this shield is also a prison. To fulfill its apocalyptic purpose, the Delta III must be able to break out of its own sanctuary. It must be able to punch a hole in the roof of the world. The operational doctrine of the Arctic Bastion hinged on a specific violent maneuver, surfacing through the ice. The R-29R missiles, for all their power, were not designed to punch through meters of frozen seawater. If the captain received the launch order while patrolling under the polar cap, he had to bring the 13,000-ton vessel to the surface before he could open the silos. This requirement turned the Delta III into an icebreaker. The maneuver begins with a search for a skylight. Using the Norca upward-looking sonar and low-light television cameras mounted on the sail, the submarine scans the underside of the ice pack. The captain is looking for a patch of thin ice, ideally less than 3 feet thick, or a polynya, a stretch of open water created by the shifting tectonic plates of the ice cap. Finding a skylight in the dead of the polar winter is an exercise in patience and acoustic interpretation. The ice is not a uniform sheet. It is a chaotic landscape of inverted mountains. Ice keels plunge deep into the water, presenting a navigational hazard as dangerous as a rock reef. The submarine must hover, inching forward, mapping the ceiling with pulses of sound. Once a suitable spot is found, the surfacing sequence begins. It is a procedure that defies the standard rules of buoyancy. A submarine typically surfaces by driving forward and using its planes to fly upward. But you cannot fly into ice. You would shear off the sail and the missile casings. The Delta III must rise vertically, like an elevator. The captain brings the ship to a halt directly beneath the skylight. He orders the ballast tanks to be blown gently, giving the submarine positive buoyancy. The massive vessel begins to rise. The impact is slow but crushing. The reinforced sail of the Delta III, hardened with extra steel and braced internally, strikes the ice first. The sound inside the hull is deafening, a screaming grind of metal against ice that reverberates through the pressure hull. The submarine shudders, the ice resists. The captain adds more air to the tanks. The upward force increases to hundreds of tons. The submarine acts as a hydraulic jack. With a thunderous crack, the ice gives way. The sail punches through, erupting into the freezing air. Huge slabs of ice, weighing tons, slide off the flanks of the superstructure. The missile deck, the massive turtleback, and follows, breaking the surface and pushing the shattered ice aside. The submarine comes to rest, listing slightly, locked in the grip of the frozen sea. It has become an island, but surfacing is only the first step. The environment on the deck of a surface submarine in the Arctic winter is hostile to human life and mechanical function. The air temperature can drop to 60 degrees below zero. The wind chill is lethal, and the missile hatches, the only exit for the nuclear warheads, are now covered in a layer of broken ice and freezing slush. This leads to one of the most surreal and gritty realities of the Soviet nuclear deterrent. The most advanced weapon system on the planet, capable of destroying cities halfway across the globe, relied on men with shovels to work. Immediately after surfacing, the ice clearance team is deployed. This is a group of sailors and warrant officers dressed in heavy Arctic gear tethered to safety lines to prevent them from slipping into the black water. They climb out of the sail and onto the missile deck. Their job is manual labor. They use crowbars, steam hoses, and even chainsaws to clear the ice from the missile silo hatches. If a hatch is blocked by a slab of ice, the hydraulic system might fail to open it, or the missile might strike the obstruction during launch, causing a catastrophic failure. The scene is almost medieval, men chipping away at the ice with hand tools on the back of a nuclear-powered dragon under the auroras of the polar night. Armed guards are posted on the sail, scanning the horizon not for NATO ships, but for polar bears, which are frequently attracted to the strange black shape that has appeared in their hunting grounds. The steam hoses are critical. Piped from the submarine's reactor plant, the steam is used to melt the ice around the hatch seals. The temperature differential is extreme, hundreds of degrees of steam meeting 60 below zero air. The deck is shrouded in a thick fog. Once the hatches are clear, the submarine is ready to fire. But sometimes the ice is too thick. Sometimes the war does not wait for a skylight. In a crisis, if the Delta III cannot find thin ice, it has a brute force solution. It carries specialized torpedoes in its bow tubes. These are not designed to sink ships, they are designed to sink the ceiling. The captain can order a spread of torpedoes fired vertically or at a steep angle into the ice above. The warheads detonate against the underside of the pack, shattering the ice and creating an artificial polynya. The submarine then surfaces through the debris field created by its own weapons. It is a violent, desperate maneuver, risking damage to the hull and the sensors, but it guarantees that the missiles can fly even if the Arctic tries to keep them down. The successful implementation of these ice operations transformed the strategic map. By the early 1980s, the Soviet Navy had perfected the art of the ice launch. They conducted exercises where Delta IIIs surfaced and fired missiles within minutes of breaking the crust. This capability made the Bastion strategy a reality. The Barents Sea and the Arctic Ocean became a sanctuary that NATO could not penetrate. For the American and British navies, the Arctic Bastion was a tactical nightmare. Their anti-submarine strategy relied on forming barriers at choke points, places like the gap between Greenland and Iceland where Soviet submarines had to pass to reach the Atlantic. But the Delta III didn't have to pass through the choke points. It stayed home. To hunt a Delta III, NATO attack submarines had to enter the Bastion. They had to sail into the Soviet backyard, under the ice, into waters protected by Soviet minefields, surface ships, and aircraft. Under the ice, the acoustic advantage of the West was nullified. The Arctic is a noisy place. The shifting ice creates a constant background cacophony of grinding, cracking, and screeching. This noise masks the sound of a submarine's engines. The thermal layers in the Arctic are complex and unstable, bending sonar beams unpredictably. A Delta III could sit motionless near the bottom or hover quietly near an ice keel and become invisible. An American Los Angeles-class submarine could pass within a mile and never hear it. The Soviet Navy reinforced this sanctuary with a combined arms approach. They didn't just leave the submarines alone, they protected them. Soviet attack submarines, the Victor and Akula classes, were assigned as bodyguards. They patrolled the perimeter of the Bastion, hunting the hunters. On the surface, Soviet icebreakers and frigates maintained a constant presence. In the air, 242 Bear patrol planes dropped sonobuoys to listen for intruders. The Bastion was a fortress with a roof of ice and walls of steel. For the crew of the Delta III, this meant that their patrols were physically safer than those of the earlier Yankee class, which had to dodge American destroyers in the Atlantic. But psychologically, the patrols were grueling. A standard patrol lasted 80 to 90 days. For 3 months, the submarine would not see the sun. The crew lived in a world of artificial light and recycled air. The isolation was absolute. Unlike in the Atlantic, where you might catch a snippet of commercial radio, under the ice there was only static. The psychological strain of the frozen fortress was managed through routine and discipline, but also through the unique amenities of the Soviet fleet. The Delta III, like the larger Typhoon, was equipped with a small sauna and a relaxation area. The sailors could take a steam bath, birch branches and all, while cruising 300 feet below the North Pole. It was a slice of Russia brought into the abyss. However, the safety of the Bastion was an illusion in one critical regard. While the ice protected the submarine from the Americans, it also trapped the submarine with its own demons. If a fire broke out on a Delta III, while it was under the ice, the crew could not simply surface and ventilate the ship. They had to find a skylight first. This delay could be fatal. A fire that might be survivable in the open ocean became a death sentence under the pack. In 1981, a Delta III experienced a reactor malfunction while under the ice. The cooling system failed. The temperature in the core began to rise. The captain had to execute an emergency surfacing maneuver, smashing through thick ice to get access to the cold Arctic air to cool the containment vessel. It was a near miss, a reminder that the fortress could easily become a tomb. Despite these risks, the Delta III proved to be a remarkably stable platform. It was the workhorse of the Soviet deterrent. While the massive Typhoon class grabbed the headlines with its sheer size, the Delta III carried the bulk of the nuclear load. They were less expensive to build, easier to maintain, and reliable enough to keep a constant rotation of ships at sea. By the mid-1980s, the Soviet Union had achieved a continuous at-sea deterrent. At any given moment, there were multiple Delta III hiding in the Arctic trenches, their missiles targeted on American cities. They were the silent, brooding guarantee that the Soviet Union could not be bullied. The Arctic operations also yielded scientific data that no one else possessed. The Soviet Navy mapped the ocean floor, the ice thickness, and the salinity gradients of the polar region with an obsession born of survival. They knew the Arctic better than any other nation on Earth. This knowledge allowed them to play a game of cat and mouse where they held all the cards. American submarines venturing into the Bastion found themselves in a maze where the locals knew every hiding spot. There were collisions, bumps in the night where steel met steel in the dark, but the Bastion held. The Delta III had fulfilled its design mandate. It had taken the nuclear warhead and hidden it in the one place where it could not be preemptively destroyed. It had turned the most hostile environment on the planet into a strategic asset. But as the Cold War ground on, a new problem began to emerge. The Delta III was invisible to radar and hard to find with active sonar in the ice clutter, but it was not silent. It was built in the 1970s using technology that was rapidly aging. The Americans were deploying a new generation of sensors. The towed array sonar systems on the new Los Angeles-class boats were sensitive enough to hear a door slam miles away, and they were beginning to pick up a specific, rhythmic noise coming from under the ice. It was the sound of the Delta III's propulsion plant. The fire from the deep was secure, and the eyes of the blind were sharp, but the heart of the ship, the engine room, was loud. The fortress was strong, but the walls were not soundproof. The Soviet engineers knew this. They knew that their workhorse was becoming noisy. But they also knew that fixing it would require a complete redesign of the hull, a cost the Soviet economy could not bear. So they decided to change the tactics again. If they couldn't make the Delta III quiet, they would make it impossible to approach. They would surround it with noise, with decoys, and with bodyguards. They would turn the Bastion into a brawl. The story of the Delta III is now from the triumph of the ice to the reality of the machinery. The boat that conquered the Arctic was about to face the consequences of its own acoustic signature. The silence of the polar night was being broken by the hum of turbines that were just a little too old and a little too loud. By the mid-1980s, the Soviet Union had achieved its strategic dream. The Arctic Bastion was secure. The Delta T submarines were patrolling beneath the ice in regular, reliable rotations, their 16 missiles targeted on the industrial heartland of the United States. The navigation systems worked. The launch protocols were automated. The deterrent was real. But inside the steel hulls of the Project 667 BDR fleet, a tactical cancer was growing. It was invisible to the eye, but painfully obvious to the ear. The Delta III was a masterpiece of missile engineering, but as a submarine, it suffered from a fatal flaw that no amount of titanium or ice could hide. It was loud. The noise was not the result of a single loose bolt or a poorly lubricated shaft. It was a structural legacy. The Soviet naval industry operated under a system of rigid 5-year plans and production quotas. Innovation was encouraged, but revolution was risky. When the designers at the Rubin Bureau created the Delta III, they focused entirely on the missile system, the D9R complex. To save time and money, they effectively transplanted the propulsion plant of the older, noisier Yankee class into the new hull. The turbines, the reduction gears, and the coolant pumps were designs from the 1960s. They were robust and powerful, but they lacked the sophisticated sound isolation rafting that American engineers had perfected for the Los Angeles and Ohio classes. When a Delta III moved at anything above creeping speed, its machinery vibrated. This vibration traveled through the hull and into the water, creating a low-frequency acoustic signature that NATO sonar analysts nicknamed the Delta drone. For the American hunter-killer submarines prowling the edges of the Barents Sea, this noise was a beacon. The USS Los Angeles class could detect a Delta III at ranges where the Soviet boat was deaf. The Americans could classify the target, determine its speed, and calculate a firing solution long before the Soviet captain knew he was not alone. This acoustic disparity created a terrifying reality for the Soviet crews. They knew they were driving the noisiest cars on the road. They knew that if the Cold War turned hot, their only hope was to be already hiding under the ice or sitting on the bottom. If they were caught in open water, they were dead. The Soviet command was aware of this vulnerability. They knew they could not rebuild the Delta III. The cost would be prohibitive, and the shipyard capacity was maxed out. So, they changed the way the game was played. They decided that if their strategic submarines could not be silent, they would have to be guarded. They developed the standoff defense concept. The Delta III would never patrol alone. It would be accompanied by a dedicated escort, usually a Victor III or Akula-class attack submarine. These escorts were the sheepdogs. They were faster, quieter, and more agile than the missile boats they protected. Their job was to circle the Delta III, sanitizing the water, hunting the American hunters. This turned the Arctic Bastion into a crowded, three-dimensional combat zone. It wasn't just a Delta III hiding in a trench, it was a wolf pack of Soviet ships maneuvering around it. The Americans responded by sending their own wolf packs. The Barents Sea became an arena of constant, high-stakes maneuvering. The proximity of these nuclear-powered leviathans led to a series of bumps in the night. The hydrodynamics of the Arctic are treacherous. The water density changes rapidly. The ice distorts sonar. And when two submarines are hunting each other in the dark, mistakes happen. In May 1981, the K-211, a Delta III returning from patrol, collided with an unknown submerged object in the Barents Sea. The Soviet crew felt a shudder, a metallic grinding that echoed through the hull. They surfaced to find damage to their horizontal stabilizer and propeller. Days later, the USS Indianapolis, a Los Angeles-class attack submarine, limped into the Holy Loch base in Scotland. Her bow was smashed. The official story was a collision with an underwater obstruction, but the paint scrapes told the truth. An American hunter had gotten too close to the prey. These collisions were terrifying near misses. If the impact had ruptured the pressure hull of the Delta III or damaged a missile tube, the result could have been a nuclear spill or an explosion that would have poisoned the Arctic ecosystem. Yet both sides treated these incidents as operational hazards, the cost of doing business in the most dangerous neighborhood on Earth. But the greatest threat to the Delta III was not the American Navy, it was the Soviet system itself. The cost of the Delta III program was not just measured in rubles, but in the physical wear and tear on the fleet. The relentless operational tempo demanded by the Kremlin, the requirement to keep multiple boats on patrol at all times, began to break the machines. Fires were the curse of the Soviet submarine force. The internal atmosphere of a sealed boat is oxygen-rich and filled with flammable materials, hydraulic oil, paint, electrical insulation. On the Delta III, the density of the equipment meant that a small fire could escalate instantly. There were incidents where high-pressure air lines ruptured, turning small electrical fires into blowtorches. There were incidents where the chemical oxygen regeneration canisters, the backup life support system, malfunctioned and exploded. The Soviet approach to damage control was brutal. The fire suppression system used a chemical gas known as freon to displace oxygen. If a fire broke out in a compartment, the standard procedure was to seal the watertight doors and flood the room with gas. This saved the ship, but it often doomed any sailors trapped inside. The crews lived with the knowledge that in an emergency, they were expendable components of the missile launch system. As the 1980s ended and the Soviet Union collapsed, the Delta III fleet faced a new existential crisis. The money ran out. The dissolution of the Soviet state in 1991 left the Northern Fleet destitute. The majestic submarines that had held the world hostage were suddenly unwanted orphans. They sat at the piers in Yagranaya and Gromyka, their reactors idling, their crews unpaid for months. The infrastructure required to maintain them crumbled. The shore steam plants failed, forcing the crews to run the reactors at the pier just to keep the boats from freezing. The specialized trains that carried the missiles stopped running. The spare parts supply chain evaporated. The Delta III began to rot. The rubber acoustic tiles peeled off the hulls. The ballast tanks rusted. The sophisticated tow-bowl navigation computers failed for lack of microchips. This period, the 1990s, was the era of the environmental paradox. The world, which had spent 40 years fearing the launch of a Soviet missile, suddenly realized that a rusting Soviet submarine was just as dangerous as an operational one. The reactors on the Delta III were filled with highly enriched uranium. As the cooling systems degraded, the risk of a leakage or a criticality accident increased. The liquid fuel in the missiles was corrosive and toxic. If the tanks ruptured, they would release a cloud of poison gas and explosive vapor. The West looked at the satellite photos of the deteriorating fleet and panicked. They realized that the Russian Federation could not afford to decommission these ships safely. Russia was broke. In a twist of geopolitical irony, the United States, Japan, and the European Union began to pay for the destruction of the Soviet Navy. Under the Cooperative Threat Reduction Program, Nun Lugar, American tax dollars were funneled into Russian shipyards. The Zvezdokha shipyard in Severodvinsk, which had built the Delta IIIs to destroy America, was now being paid by America to cut them up. The process was industrial slaughter. The Delta III were towed into the dismantling halls. Massive plasma torches sliced through the turtleback casings. The missile tubes were cut out. The reactor compartments were separated, sealed in concrete, and floated to long-term storage facilities inside a bay. Western observers watched with relief as the number of operational hulls dropped. 14 Delta III became 10, then 5, then 3. The threat was being dismantled, ton by ton. But there was a catch. The Russian government accepted the foreign aid with gratitude, but they used it strategically. By having the West pay for the expensive process of decommissioning the old Delta IIIs, the Russian Navy freed up its own limited budget. They did not use the savings to build schools or hospitals. They used the savings to build the next generation. Every dollar the U.S. spent scrapping a Delta III was a dollar the Kremlin could spend designing the Bore class. The environmental cleanup program inadvertently subsidized the modernization of the Russian strategic deterrent. The West was buying safety in the present, but financing a new threat for the future. By the mid-2000s, most of the Delta III fleet was gone. They had been turned into razor blades and reactor casks. The class had served its purpose. It had bridged the gap between the unreliable early boomers and the modern fleet. It had proven the concept of the Arctic Bastion. However, not every Delta III was destined for the scrapyard. One hull was spared the plasma torch. The Russian Navy looked at the immense volume of the Delta III, the space created by removing the massive missile tubes, and saw an opportunity. The hull was strong, the reactors were reliable. The stealth, while poor by modern standards, was sufficient for a support role. They decided to transform one of the missile boats into something else entirely. They would strip out the weapons of the apocalypse and replace them with the tools of the Shadow War. This decision birthed the BS-136 Orenburg. The conversion of the Orenburg represents the final, strange evolution of the Project 668 BDR. The missile section was cut out. In its place, the engineers installed a complex array of docking mechanisms, pressure chambers, and research laboratories. The turtleback hump, once the housing for city-killing rockets, became a hangar for something much smaller and much more secretive. The Orenburg became a mothership. Its mission was no longer to deter a nuclear war, but to facilitate special operations on the seabed. It was designed to carry deep-diving, nuclear-powered mini-submarines, vessels capable of descending to depths that would crush a standard combat submarine. This transformation marked the transition from the brute force of the Cold War to the precise, covert warfare of the 21st century. The Delta III had started its life as a blunt instrument of mass destruction. It ended its life as a carrier for spies. One of the vessels carried by the Orenburg was a deep diving station designated AS-12, known to the world by a nickname that sounded harmless but hid a terrifying capability. They called it Losharik. As the Orenburg slipped out of the shipyard, refitted and repurposed, it carried the DNA of the Delta III into a new era. The noise was still there, the old turbines still hummed, but the mission had changed. The missiles were gone. The threat was no longer coming from the sky, it was coming from the wires on the ocean floor. The story of the Delta III does not end with the scrapping of the fleet. It ends with a ghost ship carrying a secret weapon into the deep, proving that even obsolete machines can find new ways to be dangerous. In the frozen shipyards of the Kola Peninsula, where the skeletons of the Soviet fleet were being picked clean by the vultures of the post-Cold War economy, one hull was spared the torch. While her sisters were sliced into sections and their reactor compartments sealed in concrete casks, the Delta III, designated K-129, was pulled aside. She was not scrapped. She was dragged into a covered dry dock, hidden from the prying eyes of American satellites, and subjected to a radical surgery that would strip her of her name and her purpose. When she emerged years later, she was no longer K-129, she was the BS-136 Orenburg, and she was no longer a ballistic missile submarine. The conversion of the Orenburg represents the final, strange evolution of the Project 667 BDR. It marks the transition of the Russian Navy from a force of brute nuclear annihilation to a force of precise, covert seabed warfare. The engineers at the Zvezdochka shipyard had gutted the missile compartment. The massive turtleback hump, which had once housed 16 R-29R rockets capable of leveling American cities, was hollowed out. The tubes were removed, the launch controls were stripped. In their place, the engineers installed a complex array of docking mechanisms, pressure chambers, and hydraulic clamps. They reinforced the hull with titanium girders. They installed high-resolution seabed mapping sonar. The Delta III, once a warehouse for the apocalypse, had been transformed into a mothership. The Orenburg was designed to carry a parasite. Her mission was to transport, power, and deploy a smaller, deep-diving nuclear submarine known as Project 10831. To the public, this vessel was a mystery. To the intelligence agencies of NATO, it was known by a nickname that sounded harmless but hid a terrifying capability: Losharik. The Losharik is perhaps the most sophisticated engineering achievement of the modern Russian military. It is not built like a conventional submarine. A standard cylindrical hull cannot withstand the crushing pressure of the abyssal plain. To dive deeper than 2,000 meters, far beyond the reach of any NATO torpedo or sensor network, the Losharik was constructed using a string-of-pearls design. Its pressure hull consists of 7 interconnected titanium spheres. The sphere is the perfect geometric shape for resisting pressure. It distributes the load evenly. This design allows the Losharik to operate on the very bottom of the ocean in the darkest trenches of the Arctic and the Atlantic. It is a spaceship for the inner world. The relationship between the Orenburg, the Delta III mothership, and the Losharik, the deep diving station, redefined the strategic threat of the Russian Navy in the 21st century. The Delta III provided the range and the life support. It could carry the Losharik silently to any point in the ocean, hidden under the ice or the noise of the surface. Once on station, the Losharik would detach from the belly of the mothership and descend into the blackness. The mission of this duo was not nuclear deterrence, it was special operations. In the modern era, the center of gravity for global security has shifted from missile silos to undersea cables. 99% of the world's digital data, financial transactions, diplomatic emails, military orders, travels through fiber optic cables resting on the ocean floor. The nuclear archipelago of the Cold War has been overlaid by the digital archipelago of the Internet. The Losharik, deployed by the Orenburg, was built to manipulate this infrastructure. It is equipped with manipulator arms and sensitive listening devices. It can locate a cable in the absolute darkness of the seabed. It can tap it to steal information, or, in the event of war, it can cut it to blind the enemy. It can also manipulate the sensor networks. The U.S. Navy's SOSUS line, the underwater ears that track submarines, relies on cables and hydrophones. The Losharik can find them, tamper with them, or destroy them. It is a saboteur that operates where no one can see it. This shadow war is run by a secretive branch of the Russian Ministry of Defense known as GUJI, the main directorate of deep-sea research. GUJI does not report to the standard naval chain of command. It is a navy within a navy, operating with an unlimited budget and total secrecy. The Orenburg, the last surviving Delta III, became the flagship of this ghost fleet. But working at the edge of physics carries a price. On July 1, 2019, the shadow war turned hot. The Losharik was docked with a mothership. Reports vary on whether it was Orenburg or her successor, Podmoskovia, in the Barents Sea. On board was a crew that represented the absolute elite of the Russian submarine service. There were 25 officers, 7 of them were captains of the first rank, the equivalent of a full colonel or commodore in the West. 2 were heroes of the Russian Federation. This was not a routine training run, it was a gathering of masters. A fire broke out in the battery compartment. In the confined, spherical rooms of the Losharik, a fire is a tactical nightmare. The titanium walls reflect the heat. The oxygen becomes fuel. The smoke fills the spheres instantly. The details of what happened next are shrouded in state secrecy, but the outcome tells a story of supreme sacrifice. The fire threatened the nuclear reactor in the aft sphere. If the reactor vessel failed or the control systems melted, the deep diving station would be lost, and a radiological disaster would unfold in Russian territorial waters. The crew made a choice. According to official Russian statements, they sealed a civilian specialist, a representative from the shipyard, into the mothership to save his life. Then the officers sealed themselves inside the burning compartment to fight the flames. 14 men died. They died of smoke inhalation and thermal injuries, fighting a battery fire in a titanium sphere at the bottom of the sea. But they saved the ship. The Losharik was brought to the surface. The reactor remained secure. The tragedy highlighted the enduring relevance of the Delta III hull. Even in 2019, 40 years after it was designed, the basic architecture of the Kalmar class was still supporting the most advanced operations of the Russian state. The Orenburg brought the survivors and the bodies home. The old warhorse, built to destroy the world, had found a second life trying to control it. As we look back at the history of the Project 667 BDR, the legacy of the Delta III becomes clear. It is a legacy of stabilization. Before the Delta III, the Soviet nuclear deterrent was a gamble. The Yankee-class submarines had to cross the Atlantic to fire, running a gauntlet of NATO defenses that they were unlikely to survive. The Delta I and Delta II were transitional steps, capable of long-range fire but limited by their inability to launch a full salvo quickly. The Delta III Delta changed the math. By integrating the R-29R missile with the D-9R launch system, the Soviet Union achieved a guaranteed second strike capability. They could park a submarine in the White Sea under 10 feet of ice and know with absolute certainty that they could destroy the United States in 4 minutes. This certainty, paradoxically, made the world safer. It created the mutually assured destruction. Once the United States knew that a surprise attack could not eliminate the Soviet submarine force, the incentive for a first strike evaporated. The Arctic Bastion stabilized the Cold War. It turned a hair-trigger standoff into a long, frozen stalemate. The Delta III's it's not a perfect machine. It was noisy. Its propulsion plant was a relic of the 1960s. Its crews were exposed to radiation and toxic fuel hazards that Western sailors would never tolerate. But it was reliable. It worked. It went to sea, it broke the ice, and it held its station. Today, the Delta III gone from the strategic roster. They have been replaced by the Delta IV and the new Boré-class submarines. These new ships are quieter, digital, and more comfortable, but they stand on the shoulders of the Kalmar. The Orenburg remains in service, a shadowed ghost operating out of the secret bases of the Kola Peninsula. It is a reminder that the hardware of the Cold War has not disappeared. It has evolved. The missiles have been replaced by robotic arms, and the targets have changed from cities to server farms, but the game remains the same. The Arctic Ocean is quiet now. The ice shifts and groans, hiding the scars of the past. The radioactive wrecks of the K-27 and Komsomolets lie in the deep, and the dismantled reactor compartments of the Delta III's sit in concrete rows at Seabed. But if you listen closely to the hydrophones in the Barents Sea, you can still hear the echo of the Delta III. You can hear it in the doctrine of the Russian Navy, which still prioritizes the Bastion. You can hear it in the design of the new missiles, and you can hear it in the silence of the deep sea stations tapping the cables of the world. The Delta III was not the most dangerous submarine the Soviet Union ever built. The Typhoon was bigger, the Alpha was faster, the Akula was quieter, but the Delta III was the most important. It was the machine that made the threat real. It was the submarine that convinced the world that no matter how hard you hit the Soviet Union, the retaliation would survive. It was the ultimate insurance policy for a superpower that eventually went bankrupt paying the premiums. As the northern lights flicker over the empty waters of the Arctic, the ghost of the Delta III patrols on. It is a testament to the ingenuity of engineers working under the gun and to the terrifying logic that drove humanity to build machines capable of ending history just to ensure that history would continue. The ice has healed over the holes they punched. The water has washed away the oil. But the strategic geography of the world we live in today, a world defined by nuclear stalemate and seabed warfare, was drawn by the keel of the Delta III. The story of the Delta III is a study in the difference between glamour and utility. In the history books and the techno-thrillers, the Typhoon gets the glory for its sheer size and the Alpha gets the fame for its speed. But wars are not won by prototypes. They are won by logistics and reliability. The Delta III was the Ford F-150 of the apocalypse. It wasn't pretty, it wasn't quiet, but it started every morning, even at 60 below zero. There is a profound irony in the final chapter of its life. The vessel designed to launch the ultimate weapon of mass destruction ended up becoming the mothership for the ultimate weapon of mass disruption. The shift from nuclear warheads to cable-cutting drones mirrors the shift in our own fears, from the instant annihilation of a fireball to the slow, chaotic collapse of our information society. The Delta III proves that machines, like people, can reinvent themselves. But it also proves that the past never really goes away. It just goes deeper, gets quieter, and waits for a new mission. If this deep dive into the hidden history of the Soviet Navy and the strategic architecture of the Cold War meant something to you, we'd be honored to have you with us again. Until next time, stay curious and take good care.